Hello everyone, this is Abhishek Mohanty and welcome to lecture number 16 of the chapter Electric Charge and Field. Students, in the previous lecture we have discussed about the Gauss theorem and we have proved the Gauss theorem using a point charge. So in this lecture we will discuss about the first application of Gauss theorem. I had told you that there are three applications and these questions frequently come in your examination. So these three applications are very important from the exam point of view. So the first application of Gauss law is to calculate the electric field due to a uniformly charged long thin wire. So we have to derive the expression using Gauss law. Look at the diagram here. We have a very long wire, or we can say it as infinitely long wire, which extends to infinity on both sides. And this dot mark represents that the wire extends to infinity on both sides, and this wire is uniformly charged, it is positively charged. And suppose lambda is the linear charge density, lambda is the linear charge density of the wire. So this is the case of a continuous charge distribution and the charge is uniformly distributed and having a linear charge density as lambda. We have to find the electric field due to this wire at a distance r from it. Let us choose a point P which lies at a perpendicular distance r from the wire, and we have to find the electric field at this point, and we have to derive it by using Gauss law. So students, I had told you that when you are going to use the Gauss law, you have to first choose a closed surface known as Gaussian surface, and you have to choose the Gaussian surface in such a way that the angle between electric field and area vector is either 0 degree or 90 degree. So in the previous lecture, while proving the Gauss law, we have taken a point charge, and for a point charge the Gaussian surface was a sphere. But in this case we cannot take a spherical Gaussian surface, because if you take a spherical Gaussian surface then it will be very difficult to find the angle between E vector and ds vector. So for mathematical simplicity, what we have to do? So when you are going to choose the Gaussian surface, first look at the charge distribution, whether the charge is distributed over a line or over a wire, or we have a point charge, or the charge is over a plane sheet. So by looking at the charge distribution, we have to choose the Gaussian surface. So if you have a wire like this, and if the wire is charged, suppose it is positively charged, then the electric field lines will be radially outward like this. So this is the board which is 2D, and I am drawing the 3D diagram here. So you can imagine that this is the case where these are the electric field lines. Suppose assume that I have this wire, this wire is positively charged. The electric field will be radially outward along the radius. Okay, so tell me, if I choose a closed surface which will symmetrically enclose the wire, then its shape will be a cylindrical shape, not a spherical shape. If we have a point charge, then if we take a sphere, then the sphere symmetrically encloses the point charge, because all the points on the sphere are equidistant from the point charge. But in case of a linear charge, the Gaussian surface will be cylindrical in shape, like this, will be cylindrical in shape, and the wire will be the axis of the cylinder. The wire will be the axis of the cylinder. So if the wire is the axis of the cylinder, it means all the points on the curved surface, the cylinder has three surfaces, two plane surfaces, this is one plane surface, this is the other plane surface, but this is the curved surface. So if we have a cylinder and the wire is on the axis of the cylinder, then all the points on the curved surface of the cylinder are equidistant from the wire. Okay, so we saw that the cylindrical Gaussian surface symmetrically encloses this wire, the charged wire. So we have to choose a cylindrical Gaussian surface. But we have a very infinitely long wire, but we cannot choose infinite shape of Gaussian surface. So let us choose a Gaussian surface in the form of a cylinder whose radius is r, because we are finding electric field at a distance r. So the Gaussian surface, which is a cylinder, it must enclose the charged wire symmetrically. It means the wire will be the axis of the cylinder, and for that we have to ensure that the radius of the cylinder is r. We have to ensure that the radius of the cylinder is r. So imagine that this is the wire and we have chosen a cylindrical Gaussian surface. Is that clear? Now this cylinder has three faces. This is face 1, this is face 2, and this is the third face or third surface. Two plane surfaces and one curved surface. And remember that electric field due to this positively charged wire is radially outward, like this, radially outward. E vector is radially outward. Is that clear? Now, what is the left side of Gauss law? E dot ds closed surface integration. Means we have to find the integration of E dot ds over this closed surface, which is the cylinder. And the entire cylinder consists of three surfaces, two plane surface and one curved surface. So we have to divide this integration into three parts. Let us choose a small area. Let us choose a small area on the first plane surface, and let us name it as ds1. Let us name it as ds1. So ds1 vector will be given by the outward drawn normal. This is the direction of ds1 vector. ds1 vector. So electric field and ds1 vector, they are perpendicular to each other. Similarly, choose a small element here having area ds2, then area vector will be along outward drawn normal, like this. Again, electric field and area vector are perpendicular to each other. So the electric field exists at every point, but I cannot draw the electric field lines throughout the diagram. It will make it messy. So I have drawn a single line here. So keep this one as a reference. ds1 electric field perpendicular, ds2 electric field perpendicular. But if you choose an element here, if you choose a element on the curved surface, then suppose ds3 is the area of that element, then ds3 vector will be along the electric field. Is that clear? Similarly, if you choose, suppose, imagine that this is the curved surface of the cylinder. If you take a small element here on the curved surface here, then the area vector will be towards you, and again the electric field is also towards you. So E and ds are parallel. So we conclude that E and ds are perpendicular for the two plane surfaces, but E and ds are parallel for the curved surface. So we can very easily calculate the closed surface integration of E dot ds. So this is surface S1, this is surface S2, and this is the surface S3. Okay, so E dot ds closed surface integration is equal to E dot ds or E dot ds1 over the surface S1 plus E dot ds2 over the surface S2 plus E dot ds3 over the surface S3. And here don't give the closed surface symbol because we are individually finding the flux through these three surfaces, and this is not a closed surface. Okay, this is open surface. Okay, we have a circular surface here. So we have seen that E and ds1 they are perpendicular, E and ds2 they are perpendicular. So I can write E ds1 cos 90 for surface S1 plus E ds2 cos 90 for the surface S2 plus E and ds3 they are parallel to each other. So E ds3 cos 0 over the surface S3. So cos 90 is 0, so this term will become 0, this term will become 0. But the third term here we have cos 0 which is 1. So cos 0 is 1. So we will get E ds over the surface S3. Is that clear? And if you look at the cylinder, then all the points on the curved surface, are equidistant from the charged wire. It means the electric field have the same magnitude at every point on the cylinder. We have a wire like this, and this is the cylinder. The cylinder encloses, this is the wire and this is the cylinder. The cylinder encloses the wire symmetrically, and all the points on the cylinder, on the curved surface of the cylinder, are equidistant from the charged wire. Means the electric field at every point on the curved surface will have the same magnitude. So E is constant at every point on the curved surface, so I can take E outside. So E, write ds3 here, E ds3 integration of over S3. So ds3 means a small element on the curved surface of the cylinder, and if I integrate this ds3 over the entire curved surface, I will get the curved surface area. I will get the curved surface area of the cylinder. Suppose the length of this cylinder is L, and R is the radius. Then what is the curved surface area of a cylinder? It is 2 pi RL. So E into 2 pi RL is the value of this E dot ds closed surface integration, E into 2 pi RL. So this is the first half of the Gauss law. Now we will go to the next half. According to Gauss law, E dot ds closed surface integration is equal to total charge enclosed by epsilon naught. And we have calculated this part, which is E into 2 pi RL. Now we have to find what is the total charge enclosed by the closed surface or enclosed by the Gaussian surface. So look at the Gaussian surface, which is the cylinder. The length of the cylinder is L, and the cylinder is enclosing the wire. Since L is the length of the cylinder, so the length of the wire which lies within the cylinder is also L. L is the length of the cylinder, and the cylinder encloses the wire symmetrically. It means the length of the wire which lies inside the cylinder is also L. It cannot be more than L, it cannot be less than L. The length is equal to L. And lambda is the linear charge density. If lambda is the linear charge density and the charge and the wire is uniformly charged, then what is the amount of charge present on length L? It is lambda into L. lambda equal to q by L, so q equal to lambda into L. So in place of q I can write lambda into L and then divided by epsilon naught. So L will cancel, so E is equal to lambda by 2 pi epsilon naught into R. E equal to lambda by 2 pi epsilon naught into R. Is that clear? So this is the expression for the electric field due to an infinitely long uniformly charged wire at a distance r from it. And here you can see that the electric field varies inversely as the distance from the charged wire. So if you draw a graph between electric field and the distance r for this uniformly charged wire, then the graph will be like this. With the increase in distance, the electric field decreases, the strength of electric field decreases. So students, you have seen that how we can use the Gauss theorem to find the electric field due to this charged wire. In the next class, we will go for the second application. The second application is how to find the electric field due to an infinitely large non-conducting plane sheet. So till then, have a nice day and bye bye.